Alright, here we are with the answer key to the practice test. I'll try to go through it fairly quickly and get this in one sub 15-minute video. Alright, this is integration, so we're just making sure you understand basic techniques that got us started on this. We're looking at area under this curve from 0, that's 0, to 10, actually to 12 right there. So we have these 6 partitions here, and it is using the trapezoid rule. So really we're connecting endpoints with the trapezoid rule to make a trapezoid there, and then a trapezoid there, and then a trapezoid there, and so on. The way the math works out with that, we add up this side plus this side and then average that to find an average of the function, not an average of the x's, but an average of the function. So it would be right there, for instance. And it works out that the coefficients here are 1, 2, 2, 2, 2, 2, and 1. So with an even number of partitions, we will get this odd number of values, and then it's delta x over 2, because if you think about that, we've got our width, and then we're averaging our function values. Okay, so it's always going to be delta x over 2. That does not change. The delta x changes, of course, and that is going to be 12 minus 0 over the number of partitions 6. That gives us our delta x. In this case, it's equal to 2. All right. Then using the Simpson's rule, similar but different. This value is not 2, it's 3. It works out because of the math, well derived in the book, so I'll refer you to that for details. But the function, the values have coefficient of 1, 4, 2, 4, then it goes 2, 4, 2, 4, 2, 4, and then it ends with a 1 here. With an even number, in this case 6 number of partitions, that pattern will always work out to have an odd number of function values, but it'll work out with 1 and 1 at the ends and 4 at the inside values. Anyway, you can check out, they're both pretty close, and that's just how you do it. So this is fairly simple in that we're looking at a region underneath this parabola. What this is all about is just understanding that an integral comes from a limit. As our partitions get infinitely thin, infinitely small, we write it like this: the limit as n approaches infinity. We're summing up these partitions, the areas from 1 to n then, and this f of xi just represent how we count our way through those partitions. So the notation gets a little bit dense, but when we work out that each slice as we count our way along is found by taking that delta x and then going the first delta x and the second delta x and the third delta x. This is our index number, that then the final summation notation looks like this. We pull out the delta x because that's just a constant, whatever that is. That's not a variable. The variable is the I that's changing in this case, and we count our way through and we square it because that's our function, minus 4 times that delta xi, and then plus 5, and we're just summing up from 1 to infinity. Alright, so that's really what we're looking for here. Part B is estimate the area under the curve by taking sample points to be midpoints, and again, it's just in this case we're averaging the two x values. So if we know we're taking just 4 subintervals, alright, then in between 0 and 1/2 will be 1/4, in between 1/2 and 1 will be 3/4, and so on. And that comes from the fact that we're going from 0 out to 2 with the 4 subintervals. So again, we get 2 minus 0 all over the 4 gives us a delta x that's equal to 1/2. Okay, so that's where that comes from. That 1/2 right there comes from that little equation. And then we can check our approximation by actually finding the area under the curve, because you know your integration techniques. So we set up the integral, we go through it, and it turns out that it's exactly 4 2/3. Alright. So problem number 3, just testing your ability to find some of these integrals. Fairly straightforward. As you look at this, don't be tempted to think integration by parts. The plus sign there is a huge hint that you're simply splitting these two separate things apart if you need to, and then doing this separately. But in this case, we can divide the x to the 1/2 into the x to the 5th, and x to the 1/2 into the x, and I could put it decimally like x to the 4.5, but it's just as easy to do it with fractions. And remember the reverse of the power rule. We figure out what that exponent would be by adding 1, in this case 2/2. It takes us to 11/2, and then we have to have the reciprocal of that, so when we bring it out front it cancels, cleaning up the fractions, and we get this fairly straightforward. Hopefully that's easy points. Here we have one that is not quite so straightforward, but as you think how can you simplify this, you're either going to do this by parts or by substitution. The key thing for substitution is if you can find a part of this elsewhere. In this case, the derivative of this is 1/x squared, square root of x, with a little, clean up that little coefficient, that 1/2. We can pull that out front, and we get this is exactly what we find right here. Okay, so, or I guess I should include that. So then we can do this. I started off to set it up as if it was by parts, but you can see that that does not work. It is simply u substitution. When we make that substitution, we pull that 2 out front, and we simply get sine of u du. We can take that derivative, or that integral, and the integral of sine is minus cosine, and then the negative sign comes out front, and then we go back in and sub, and we don't forget to add the plus c. So our original substitution, of course, we want to replace it in this case and answer as it was given. If it's a definite integral, we can leave it in the u form and go on from there, but this one isn't. On to page 3. This one requires a few more decisions to be made. You look at this and you want to look at the degrees. Okay, if the degree is less up above and down below, you absolutely want to see if you can factor and cancel, and then maybe go directly to partial fractions. But in this case, because the numerator has a higher degree, you want to divide that denominator in. In this case, all we can pull out of it through polynomial long division is x minus 2, with this remainder being x minus 14. Okay, so we can separate this into really 3 parts, 1, 2, and this third part here is partial fractions. This I can factor. It factors to be x plus 3 times x minus 4, which is why it appears down here. And so I have split it, whoops, right here. I just busted out. This is the partial fractions part, where I know that there's going to be some a, or at least I hope there's going to be some a over this factor plus b over this factor that will give me that rational expression. All right. So 2 ways to solve. You can either distribute the a's in and then write 2 systems of equations based on the x's and the numbers. It's just as easy to think of a value, in this case -3, that gives this 0. And when that's 0 and I plug in -3 there and -3 there, I get a fraction that I can then solve. I'm sorry about the bouncy camera. And I get an ugly fraction, but we're not going to be scared by that because we just pull it out. When I have x is equal to 4, then that bit drops out. When x is equal to -3, that bit drops out. I solve each of those. I get my a and my b, and I put them back in up here in my split apart partial fraction form. Those constants just come out front, and I get then 17/7 ln of x plus 3. And then I would evaluate that because this is a definite integral. All of these are definite integrals, and I've just done that one there, fairly straightforward, and here, and you wind up with this expression. I think there's no point really. You could bring them in and combine them, but at that point it's pretty simple to write and be very simple to enter into your calculator. I guess I should type that and put that into 3 decimal places, but I won't do that for you now, but that would be pretty easy to do. Okay, moving along, this is an improper integral because it's going up to infinity. We need to do this one by parts. There's no simple substitution that will appear in the dx part, so I'm going to make my parts substitutions for u and v according to the Lyautey rule. So I just use the algebra here to go first. So u is equal to x, du is dx, pretty simple. The leftover bits then right here becomes the dv, so I integrate, relatively straightforward there, and then I just remember that my integral becomes these two things multiplied, and then the integral with these two things when you write it that way. You're always taking the derivative to go down and integrating to go up. I think that structure helps make it a little bit easier. So what do we have? We've got this times this right here. Whoops, sorry. This times this right here. I've got the minus sign out and I just put the x up above. Then minus the integral, but that minus sign makes the minus minus a plus. I do this integration and it's quite straightforward. It's minus 1/9 e to the minus 3x. Then I've got I'm writing this as a limit as n goes to infinity from 0 to n, and as I break this down here, it's still a limit. I'm putting in n into my places for x and then working out what that actual limit is. These middle ones go to 0 as e here goes towards infinity. It's actually, I'm plugging in 0, I'm plugging in 0 there, so that goes to negative 1/9. This one, however, is in the form of infinity over infinity when I write it with that denominator going to n, and so I need to use L'Hopital's rule. When I take the derivative of the top and the derivative of the bottom, it's very clear that now the bottom is exploding to infinity, which means that the whole thing is going to 0. So my actual answer then is a minus 1/9, which gives me 1/9 as that answer. Okay, I got 3 minutes to do the last page here, keep it under my 15 minutes. And this one is another problem. Again, it's using parts. Again, we do not see a simple u substitution here where I make a substitution for 1 and get it in the derivative part. So following the rule of L'Hopital a second time, I've got algebra and then I've got logarithmic. So this time L comes first. So this is my substitution. U equals ln of x. Du then is 1 over x dx. My dv are the leftover bits, and I integrate that to find my v, and then I just do the same thing I did before. I multiply these top two, there they are, and then subtract the integral. I pulled out that 2/5, and now I'm going to clean up the x to the 5/2 power times 1 over x, so I'm subtracting 1 from 5/2 and I get this part. So that's really what that integral becomes. So here it is then, the explanation for that. I can take that integral quite easily because it's the inverse of the power rule. There's my integral. I've got my bounds. I sub in and I process and I wind up with the exact answer, 64 over 5 ln of 4. This one I did put into my calculator, and that's what I got. On to number 5. Just again, hoping that you can relate what these integrals are all about in terms of real-world application, get your units straight. That should be pretty simple. There might be applications in physics with velocity, right? So when we integrate a velocity, we're going to get a distance, okay? Use your knowledge of geometry here. This is just a semicircle. Again, what does this notation mean? It's just saying, all right, we've got this function that is defined from -3 to 3. That's our domain, and we get a semicircle. So clearly we can just use our knowledge of the geometry to write the expression. You do not have to go through and integrate this the way we did in class. That's complicated. Hopefully that's clear. Just using your knowledge of geometry, you know that's a semicircle, so just do 1/2 pi r squared. And finally, just do your best to understand really what the big picture is. What is that fundamental theorem of calculus saying? How it relates the inverse operations that are the derivative and integral. Okay, so do some reading on your own. See if that makes sense to you. All right, good luck.